In this video, we are going to continue to explore the big idea of properties, and we're going to be talking about factoring some trinomials such as squares of binomials or differences of two squares that can be factored by using rules that are the reverse for multiplying special case binomials. And we're going to take a look at what that means in the coming slides. Basically, we're looking today at factoring something called the difference of squares. So the product of a sum or a difference of the same two terms is the difference of their squares. So if you take a look here towards the center, we see that if we were to multiply a plus b and a minus b, we would end up with a squared minus b squared. And this really is the key to today's lesson. Let's take a look at a couple of examples here. Just like we did in the factoring by GCF video, we are going to take a look at some multiplication first. So on the left side of this screen, if we were asked to multiply x plus 2 and x minus 2, we would use a process that kind of repeats the distributive property twice, and the acronym that you know to remember that is FOIL. So let's FOIL these things together. X times x is x squared, x times negative 2 is minus 2x, 2 times x would give us plus 2x, and then 2 times negative 2 would give us minus 4. We can put the center two things here together because they are like terms. So combining those, we get x squared minus 4. On the right-hand side of the screen, we're actually being asked to factor x squared minus 4. And we want to go back to this piece right up here that shows us that when we have two things with opposite signs in the middle, that it's going to give us that a squared minus b squared. So looking at x squared minus 4, we hopefully recognize the x squared and the 4 as perfect squares. When that happens, we go back to the rule up top, and we take the square root of each term. The square root of x squared is x. The square root of 4 is 2. One set of parentheses is positive, and the other is negative. Let's look at a few more examples. Factor completely x squared minus 36. Are x squared and 36 both perfect squares? They are. Means that we're going to have our two sets of parentheses. Square root of x squared is x. Square root of 36 is 6. One set's positive, one set's negative. Doesn't matter which set of parentheses each sign goes in as long as you have one that's positive and one that's negative. Moving along, x squared minus 121. Are both terms perfect squares? In this case, again, they are. Square root of x squared is x. Square root of 121 is 11. So our factored form is x plus 11 and x minus 11. Next example is a little bit tricky. If we take a look at 2x squared minus 18, neither one of those are perfect squares. And this takes us to a really important lesson we have to learn about factoring. The first thing you always do is look for a GCF. So take a look in this problem. What's the GCF of the terms 2x squared and 18? Our GCF here is 2. So when we factor out the 2, we're left with an x squared minus 9. And this is a great example of the directions, factor completely. In this case, when we look at what's left inside the parentheses, we should hopefully see that x squared and 9 are perfect squares. So we're going to leave our GCF of 2 on the outside, and the x squared minus 9 factors to be x plus 3 and x minus 3. Taking a look at our last example, x squared plus 9. Are x squared and 9 perfect squares? They are. But you have to ask yourself, what's different about this problem than what we've seen before? The difference is subtle, but it's really, really, really important. This plus sign means that the polynomial cannot be factored. There was no GCF for us to factor out, and we cannot factor the sum of squares. The method was called the difference of squares. That means that you have to have two terms that are being subtracted, and those terms must be perfect squares.